every element is made up of atoms. In the atom, you have a nucleus where you have protons and neutrons, and that's where the majority of the mass of the atom. Surrounding those nuclei, we have electrons. Now, we have probably picked up already that in a periodic chart, the atomic number, the one numbers in virtually every periodic chart, is simply the number of protons in the nucleus. It identifies the atom. For instance, carbon has atomic number 6, so carbon has 6 protons, and every one, just think of all those millions and millions of atoms in a small pile of carbon. Each atom has 6 protons. That makes it carbon. But we have this strange number that you see 12.011. You'll see no number or no unit attached to this number. The unit happens to be AMU, atomic mass units. And this is really gobbledygook. How's that for a scientific term? The number is not well understood by students. Students can pick up the number of protons very quickly. Well, this is called the atomic weight or the atomic mass. Atomic weight or atomic mass, and most people nowadays prefer to say mass. This atomic weight was first discovered empirically in about 1826 in terms of the history by a sometimes called the second father of modern chemistry, a Swedish scientist by the name of Berzelius. But the modern day atomic weights are determined through a process called using mass spectrometers. And here's the issue. 12.011 comes from the fact that nearly all elements are made up of isotopes. In other words, these are atoms that of the same element have the same number of protons. But a different number of neutrons. Different neutrons. For instance, carbon-12, or carbon, is made up of atoms that are called carbon-12, carbon-13, and carbon-14. These are called the natural isotopes. You can also make isotopes in nuclear particle accelerators, we'll talk about later. So somehow the combination of these different atoms come up with this value 12.011. Now how is it done? Well, in the mass spectrometer, you can weigh elements, atoms, to 6 decimal places. You couldn't begin to weigh atoms on any kind of a balance. It's impossible, for they're so small. But what it does is it charges particles. And the idea is if you have a heavier particle sending through a magnetic field, it will be deflected. The heavier particle is deflected less. So carbon-13 will be deflected less than carbon, and I'm exaggerating, carbon-12. Now, carbon-14, there's such a small amount that we're going to ignore it right now. It's called trace, it's insignificant. So in a mass spectrometer, this ratio, this deflection ratio, can be measured to a great precision. And the deflection ratio between carbon-12 and carbon-13, the mass ratio, is this strange number, and I'm going to write it down. You never memorize this. It's 6 decimal places. This is the deflection ratio. So if you want to get a value, what in 1961 they said, we're going to say that carbon-12 is going to be exactly carbon-12 with an infinite number of zeros. It's called an exact number. So carbon-12 would be a value of 12.0000 forever, an exact number. No significant figures because it's exact. So you could take carbon-13 and compare it to carbon-12 by multiplying it by the exact carbon-12 value here of 12 AMUs. And we're going to talk about what an AMU is equivalent to in a minute. And we come out with a mass of the carbon-13 is 13.003355. So every atom, every isotope is going to have this strange, highly precise number. Well, in nature, there's a distribution of these isotopes. And in nature, carbon-12 is 98.9889, which is 98.89% of nature is carbon-12. Almost all of carbon is carbon-12 in nature. So if you take this percentage times the exact value of the mass of 12 AMUs, plus for carbon-13, if you take the percentage left over, which is let's see, we get this right, 0.011, is that right? And multiply that by the weight of carbon-13, and for practical purposes, I'm just going to put a 13 down here. See, it's 0.003. And when we put these together, we come up with 12.011 AMUs. Now let me go back, because you're saying, boy, that's a lot of numbers. Here's the deal. All atoms can be weighed to a high degree of precision. The problem in this approach is there is a low degree of precision in these percentages right here. This is a natural percentage. This is called the occurrence, or the percent in nature. In fact, in just last Christmas, December 1910, they found out that carbon varies so much in nature that they now have a percentage around 12.011. They're bracketing atomic weights. It's not on most of your charts. Again, you don't remember this. But this is how they're presenting the atomic mass of carbon now, from a low to a high, depending upon the range of percentages in nature. Well, this is the weight of a single composite atom. This atom does not exist in nature. Do you hear that? It doesn't exist. It's a composite weight. So if you wanted to get the weight of this composite atom, you would take 12.011, and you would have to know, if you wanted it in grams, you'd have to know a conversion factor, and you'd have to use dimension analysis. And you put AMUs here and grams here, and you can make the conversion. And believe you me, it's extremely small. We'll be talking about that later. Very small. And we will stop right there, and we'll continue in